Hi, it's Miss Reese. I'm going to be going over a few problems on what is this, page 19. So this is just some extra practice of the problems finding the area of regular polygons. So this time you're just given one measurement and you have to use trig to find another measurement. So I like to always kind of set up my problems by creating my little right triangle in each of these. Let's pretend, try it again. Let's pretend that's a straight line. So two things I need to know. I am going to highlight this triangle here. And if I can find the area of this triangle here, I should be able to find the area of the entire shape. Now I can fit two of those triangles, 1, 2, on each side of this pentagon. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can essentially fit 10 of those highlighted triangles in the entire pentagon. So we'll set up the problem and then we'll figure out what we still need to find in terms of the area. So I've got area is equal to, we know area of a triangle is base times height. Well, we don't know the base yet. Let's see, what is the height of that triangle? The height could be 10, and I guess the 10 could be the base depending on which way you're looking at it too. And then we said that there are 10 of those triangles, 10. So this is the number of triangles, or I'll just put number of triangles here. Remember, a triangle is base times height divided by 2. So in order to solve for that base, that's this length right here, we're going to need to use a trig ratio. So you can call it b for base, we can call it x, you can call it any variable you want. Since I already labeled it with a b here, I'm going to call it the base. And so what we're going to do, I'll draw out that triangle kind of off to the side here just so you can see it a little bit better. We've got our height here, which is 10. We've got this base that we're solving for. Now, in order to use trig, a sine, cosine, or tangent ratio, we really need an angle from there. So I know a full rotation is 360 degrees. So these angles here we can find by taking 360 and dividing it by twice the number of sides we have. So we're dividing it by 10. And that's because those angles, just like we can fit 10 of these triangles in the shape, we can fit 10 of these angles in the center of the shape. That's a half central angle. So that angle is going to be 36 degrees. So now we say, okay, from that 36-degree angle, okay, we're figuring out, is this going to be using a sine, cosine, SOHCA, or TOA, sine, cosine, or tangent ratio. And from 36 degrees, this side is opposite, it's across from, so this is an opposite side, and we've got this side which is next to the 36 degrees, that's an adjacent side. So that would be a tangent ratio. So to solve for that b value, we could say that the tangent of 36 is equal to the opposite side b over the adjacent side 10. Once you set up your cross product, you solve for b, you can substitute that right in here and you will get the total area for that shape. Okay. On question 2, you're going to do something similar for that. Now this does create a special right triangle because when you do the half central angle, if we're looking for this angle here in the middle, I would take 360 and I would divide it by, this time I divide it by 12. I have 2 of these little triangles or angles per side, and there are 6 sides. So I'm going to divide it by 12. And that's going to give you a 30-degree angle for the middle there. So you can rotate this triangle around if you want and kind of just redraw it. We've got our 30 degrees here. That's the top angle. We've got this length here, which is 5, and we're solving for, we can call it b again if we want. And we can, once we've solved for that side, we can use that to find the total area. Now, if you want, you could use a special right triangle property, but I would just go ahead and use sine, cosine, tangent. Next week, we are going to be looking on the special right triangle properties. So I would just continue this problem just like you did the first one. Okay. And question number 3. So these are all similar because we are starting out with the same type of segment length. We're starting out with that apothem. It's really the triangle height, distance from the center of each of the figures to the midpoint of one of the sides. So questions 1, 2, and 3 are going to be set up in a similar way. On to question 4. The difference here is that you're starting with a side length, and that's a full side length. You still do need to create like our little half triangles here. So when creating that half triangle, we still have to find the angle in the middle. So we can find that angle in the middle, taking 360, dividing by twice the number of sides we have. There's 2 of those angles per side. And then when you draw out that little half triangle, if it's a half triangle, this length here is going to be half as well. So this is going to be a 4. And then we would have here, this is the height that we're solving for essentially. Okay, so I'm going to call it x because I don't want you to get confused with height and hypotenuse and whatnot. So I'm just going to call it x. You're going to solve for that. And we've got 36 degrees here. And so we've got our opposite, we've got our adjacent. And remember, anytime you're setting up a tangent ratio and your variable is in the denominator, let's actually do this one. This is opposite and adjacent. Oops. So this would be a tangent ratio. So we could say tangent of 36 is equal to the opposite side 4 over the adjacent side x. Now remember, when we do our cross product here, x is going to multiply to tangent of 36. And that's going to equal 4. Now, the only way to get x by itself, right now it's being multiplied by a tangent, you can divide it by a tangent on both sides. So once we know this length here, the height, we have the base of this triangle, we have the height of this triangle. Base times height divided by 2, that would be the area for just this one little triangle. And then you just have to multiply by how many of those triangles fit into the shape. Okay. That process will be the same for question 5. The only difference will be the angle. The central angle is going to be different. And then question 6 is a little more challenging. You actually need to find 2 missing pieces on question 6. So the length that you're given here is a radius. That's from the center of a figure to one of the angles. That's the radius. And we call it a radius because if you imagine like creating a circle that goes around this, that's the distance on a circle too. Okay, well, that's our next unit. So with that radius, I'm actually going to draw it here as well, just so you can see the triangle kind of oriented in a little bit easier way. So this is the triangle I'm going to focus on. The radius from the center to the angle, this is still 19. Okay, and this time we need to solve for both of these sides here. We'll call one of them x, we'll call one of them y, and I'm going to put my right angle symbol here. Now my angle at the middle of the figure, this is still a pentagon, so the angle would be 360 divided by twice the number of sides I have, so it's 10. That's a 36-degree angle. Now when setting this up, I would set up and kind of solve these separately. So in the first problem here, we've got 36 degrees, we've got 19, we've got x. So figure out, okay, is this a sine ratio, a cosine ratio, or a tangent ratio? And almost think of that as a separate problem from here with y. We've got 36 degrees, we've got 19, we've got y. Once you know the value of x and y, all you need to do is find the area of that triangle. X and y are the base and height of that triangle. So we've got base times height divided by 2, multiplied by how many of these little half triangles fit into this entire pentagon.